Dengue has been a vastly spreading disease in Sri Lanka. According to the statistics of Epidemiology Unit of Ministry of Health in Sri Lanka, 125 people have died due to dengue in 2019 and 2020. There is no medicine to cure dengue fever. The currently practiced method is to keep the dengue patient in the hospital and hourly measure the urine output and, according to the measurement, adjust the input fluid volume given order to the patient. Currently, urine output is manually collected by a hospital attendant or a caregiver for the patient. In some cases, this measurement is taken by the patient himself. During period of outbreaks, the number of patients can be very high, and the manual measurement could cause overloading of the healthcare workers and it may lead to inaccurate measurement. This repetitive manual measurement process is a heavy burden to the already tired and overworked hospital staff during such outbreaks. Our objective is implement a device to automatically measure the urine volume which can be used in a hospital environment. Our solution for the above identified problem is an IoT-based urine volume meter. When considering the system overview of the device, we have the electronic circuit powered by the power unit and the input is given by the sensor unit. Then the signal is passed to the processing unit through an analog to digital converter. Also there is a user input unit and a display unit to display the result. The process signal is passed to the internet server through a communication unit. The results are subjected to analysis and visualization. All the results are stored in a storage unit as well. The thermistor is connected as an arm of instant bridge. The amplified voltage drop signal is used to change the current through the thermistor using a negative feedback loop to operate the thermistor in constant temperature mode. When fluid drop falls onto the thermistor, the current needed to heat the thermistor to keep the temperature constant produces a measurable signature in the output voltage waveform. This voltage signal is processed to detect the event of drop falling using a signal processing algorithm. A simple signal processing algorithm was used to detect urine drops. In here, the input amplified signal is sent through the several moving average filters and derivative blocks. Finally, the resultant signal is sent through the peak finding function and measure the volume by counting the urine drops. The amplified signal is not enough to detect the urine drop due to noises, so we need to process the signal to eliminate noises. With the purpose of identified drops, the smooth derivative signal was taken by sending through a derivative block and a moving average filter. To improve the detection accuracy, we send the signal again through a moving average filter and a derivative blocks as shown in step 3 figure. In step 4, urine drops can be identified without any mislead using the drop detection by thresholding. Finally, the total urine volume is derived using the signal processing algorithm. After getting urine volume, we have used two methods to represent and analyze the output data in an IoT platform. ThinSpeak IoT platform was used to analyze the data and a website to visualize data. The cloud-based data visualization channel was designed by using the ThinSpeak IoT platform. Real-time processed data was sent to the above IoT platform by using ESP8266 Wi-Fi module. Key features analyzed in ThinSpeak are patient ID, variation of drop size in sample time interval, variation of urine drop count, current urine volume, total amount of urine volume, and so on. A PC-based application is used as the input system to the device. Patient ID and Wi-Fi configurations can be configured using this application. The website introduced to display the patient data and urine result in a user-friendly way. Patient and authorized staff members can only access the website. Perfuser compact infusion pump was used to send 5 ml of water at a fixed flow rate. The theoretical average drop volume is 0.05 ml. But according to the result of the above calibration, the average drop volume is changed with flow rate. The average size of a drop was calculated as 0.0614 ml using above calibration. This graph shows the standard deviation of the drop volume for some of the different flow rate and how the drop volume vary with the flow rate. According to this result, we can see that the 5 ml volume can be achieved by using the mean drop volume 0.0614 ml. But it is not achieved with the theoretical value 0.05 ml. So from that, we can verify that using 0.0614 ml gives more accurate result. This is the prediction error percentage variation with flow rate. Above blue line indicates prediction error percentage variation for theoretical drop size 0.05 ml. It has more than 15% error for every flow rate. Other line indicates prediction error percentage variation for different type of experiment result. All these lines are in plus or minus 5% error bound. So we can conclude that calibrated mean drop size is more accurate than theoretical drop size.